Welcome to the deep dive. Today we're tackling something that sounds, well, maybe a bit technical on the surface, preheat in welding.
Right.
But stick with us, because we're going to show you why it's actually incredibly important and pretty fascinating too.
Okay.
Okay, let's unpack this. Our goal here is to figure out why adding heat before you even start welding is such a game changer. We're talking durability, safety, things that really matter for, bridges, pipelines, all sorts of structures you encounter. So let's just kick things off. What does preheat actually mean when we're talking welding? Is it just like warming up leftovers, or is there more to it?
Definitely more complex than leftovers. Basically, preheat is applying heat to the joint, the part you're about to weld, immediately before you start welding. You typically use something like a gas torch, maybe an induction system. There are other ways too, and it's usually specified as a minimum temperature you have to hit. Sometimes, it's a range, but minimum is key.
Okay, a minimum temperature. So why? Why go to that trouble, especially with steels? What's the big advantage?
Right, well, the why is crucial. There are several big reasons. First off, it really helps get hydrogen out of the weld area.
Hydrogen, why is that bad?
Hydrogen is a welder's enemy. It can cause cracking later on, so getting rid of it is a major plus. Second, preheating slows down how fast the weld and the area right next to it, the heat-affected zone, or HAZ, cools down.
Okay, slowing down the cooling.
Right.
What does that achieve?
It's really important because it reduces the chances of forming brittle microstructures. The classic example is martensite.
Martensite, sounds nasty.
It is. It's very hard, which sounds good, but it's also very brittle, like glass. So it's prone to cracking under stress. Slower cooling avoids that, and that slower cooling also gives any hydrogen that did get absorbed more time to escape, to diffuse out. Again, less risk of cracking.
Got it. So less brittleness, less hydrogen cracking. Anything else?
Yep, couple more things. It helps remove any lingering moisture from the area you're about to weld. Water and welding don't mix well. It also generally improves the fusion characteristics when you're actually welding. Things just flow together better. And finally, it helps make sure the expansion and contraction are more uniform. Less stress between the weld and the original metal.
Wow. Okay, so it's not just one thing. It's tackling hydrogen, brittleness, moisture, fusion, stress. Sounds fundamental.
It really is. It's about controlling the material's response to the intense heat of welding right from the start, building an integrity.
Okay, so preheat temperature is that initial minimum. You mentioned temperature control is key. Are there other temperatures we need to know about during the process?
Yes, absolutely. Precision matters throughout. So besides the preheat temperature itself, the temperature right before any welding even tack welds, you also have the interpass temperature.
Interpass between passes, I guess.
Exactly. If you're doing multiple weld runs, it's the temperature of the weld area during the welding and just before you lay down the next bead or pass. And crucially, it includes the adjacent parent metal too. Now, this one is usually given as a maximum. You don't want things getting too hot between passes.
A maximum. Interesting. But it shouldn't drop too low either.
Right. Critically, the interpass temperature must not fall below the minimum preheat temperature you started with.
Okay, that makes sense. Maintain a certain warmth. And you mentioned one more.
Yes, the preheat maintenance temperature. This is the minimum temperature you have to keep in the weld zone if welding gets interrupted. If the welder stops for lunch or something, the piece can't be allowed to cool down below this maintenance level.
Got it. Preheat, interpass, maintenance, lots to keep track of. How are these specific numbers actually figured out for a particular job? Is it just gut feeling or pure science?
Oh, it's definitely science, though experience helps apply it. For steels, it's calculated based on several factors. Key ones are the carbon equivalent, or CEV.
CEV, what's that?
It's basically a way to figure out the steel's hardenability, how likely it is to become brittle or crack based on its chemical composition. Higher CEV often means more preheat needed. Then you factor in the material thickness. Thicker generally needs more heat. And also the arc energy, or heat input from the welding process itself, measured in kilojoules per millimeter. Different processes put in different amounts of heat.
So CEV, thickness, heat input, sounds like a formula.
Pretty much. Standards like BSEN 1011 give you the methods to calculate it. Interestingly, though, for a given CEV and heat input, the preheat needed might stay about the same for thicknesses up to maybe 20 millimeters or so. But ultimately, the person doing the inspection, the welding inspector, doesn't usually do the calculation. They find the required temperatures specified in the WPS.
The WPS.
Welding procedure specification. It's like the recipe book for that specific weld. It tells you everything, including the required preheat and interpass temperatures.
Okay, the WPS is the guide. Now, moving to the practical side. How do you actually get that heat into the metal, especially on big pieces out in the field or in a workshop? What methods are used?
Good question. There are quite a few ways, and they sort of fall into two main camps: local application and global application.
Local and global.
Yeah. Local application means heating just the weld zone and the area immediately around it. It uses less energy overall. Common methods here are things like gas torches, very common induction heating systems, resistive heating elements, which are like electric blankets using coils.
Induction, like the cooktops.
Sort of, yeah.
Yeah.
Same principle, using magnetic fields to generate heat directly in the metal. Very efficient. There are also high-frequency heating elements and just general flame heating. The potential downside of local heating is that you can sometimes introduce stresses because one part is hot and the rest is cold.
Ah, okay, so what's the alternative? Global.
Right. Global application means heating the entire part, or a very large section of it, uniformly. Think big gas or electric ovens. This uses more energy, obviously, but it gives you very even heating, which avoids those extra stresses caused by temperature differences, often used for really critical or large components.
Makes sense. You mentioned flame heating is probably the most common for local preheat.
Yeah, I'd say so. Using torches or burners with a fuel, gas, acetylene, propane, natural gas, and oxygen. The really critical thing with flame heating, though, is allowing enough time for the heat to soak through.
Soak through.
Yeah, you need the temperature to equalize right through the thickness of the metal. If you
Yeah.
just heat the surface quickly and measure it, you might get a reading that looks right.
But the inside is still cold.
Exactly. And that defeats the purpose. You haven't achieved the real benefits of preheat deep down where it matters for the weld structure.
That seems like a crucial detail. So once you've applied the heat, say with a torch, how do you control it and measure it accurately? Where exactly do you stick the thermometer, so to speak?
Precision is key, like you said. First, when to measure. Immediately before the arc is struck for each weld pass, right before welding starts. Now, where you measure depends on how thick the metal is. If the workpiece thickness, let's call it T, is 50 millimeters or less, you measure on the surface facing the welder. And you measure within a specific zone. 4 times the thickness, 4ct, away from the edge of the weld preparation, but capped at a maximum distance of 50 millimeters.
Okay, 4T up to 50 millimeter max. On the welder's side, what about thicker stuff?
If it's greater than 50 millimeter, you measure within a minimum distance of 785 millimeters from the weld zone. And importantly, if it's practical, you actually try to measure on the face opposite the one being heated.
Opposite. Why is that?
That helps confirm the heat has soaked all the way through the entire thickness. It's a better check for thick material.
Got it. And interpass temperature, where is that measured?
Interpass is measured right on the weld metal itself or on the parent metal immediately next to it.
And you mentioned soak time earlier. Is there a rule of thumb for that?
Yes. A common guideline is to allow about 2 minutes of soaking time for every 25 millimeters, or roughly 1 inch, of material thickness after you think you've reached the temperature. Ensures it's even.
2 minutes per inch. Okay. These are really specific rules. What tools are actually used to take these measurements? Are we talking fancy lasers or something simpler?
You actually have a range of tools, from quite simple to very sophisticated. On the simple end, you have temperature-sensitive materials. You might know them as temple sticks or thermochrome paints.
Temple sticks?
Like crayons. Exactly like crayons.
Yeah.
Special wax crayons designed to melt at a very specific temperature. Or paints that change color permanently. They're cheap, super easy to use. The big downside, they don't tell you the actual temperature.
Just if you've hit the target or not.
Right. It's a go-no-go indicator for that specific crayon's rating. Useful, but limited.
Okay, what gives you an actual number?
For that, you'd use something like a contact thermometer. These often use a bimetallic strip that bends with heat, or maybe a thermistor, a resistor whose resistance changes predictably with temperature. They're pretty accurate, give you a real temperature reading, but they need calibration and are usually for, let's say, moderate temperatures, maybe up to around 350 degrees Celsius.
Okay. What if you need higher temps or more precision?
Then you're probably looking at thermocouples. A thermocouple is basically 2 wires made of different metals joined together at one end. When you heat that junction, the tip you place on the workpiece, it generates a tiny voltage, a thermoelectric effect. And that voltage corresponds directly to the temperature.
Clever.
Yeah. They're accurate over a wide range, give you the actual temperature, and you can even hook them up for continuous monitoring during welding or heating. They do need calibration too, though.
And the fancy laser things.
Huh? Yeah, the contactless ones. Those are optical or infrared pyrometers. They measure the heat radiation coming off the hot surface. Great, because you can measure from a distance, which is good for safety or very high temperatures. But they are generally much more complex, quite expensive, and usually reserved for higher temperature applications or specialized situations.
So quite a toolbox from crayons to pyrometers. It really drives home how critical getting that temperature right must be. Okay, let's try and pull this all together. For someone whose job it is to make sure this is done right, like a welding inspector, what's the absolute key takeaway message?
The single most important thing. Always, always refer to the welding procedure specification, the WPS. That document dictates the required preheat and interpass temperatures for that specific weld, period. If there is any uncertainty, any doubt at all about how or where to measure, don't guess. Consult a senior inspector or a welding engineer. Get clarification. And remember, this isn't just good practice. Preheat and interpass temperatures are almost always essential variables in welding codes like BSEN, ISO 15614, or ASME 9.
Essential variables. What does that mean practically?
It means if you change them outside the range that was qualified during the procedure test, the whole WPS is invalid. You'd need to qualify a completely new procedure. It's that fundamental to the weld's integrity.
No. Okay. Non-negotiable then. This has been incredibly illuminating. We've gone from a simple term, preheat, to understanding its deep impact on metallurgy, safety, and the longevity of welded structures. It really makes you appreciate the invisible science that goes into making sure that the things we build and rely on are actually strong and safe. It's not just sticking metal together.
Absolutely. And if you think about the bigger picture, how many welded things do you interact with every single day? Your car, buildings, bridges, maybe even pipes underground you never see. And their safety, their ability to function for decades might hinge on someone carefully controlling a temperature with a crayon or thermocouple before the main event even started. Kind of makes you wonder, doesn't it? What other hidden, meticulous processes are underpinning the safety and reliability of our world that we just, take for granted?
That's a great point. Here's where it gets really interesting. Maybe the next time you see a large steel structure, you won't just see metal. You might think about that silent, precise dance of heat and material science that happened long ago, making it strong enough to stand the test of time.
Our examination appeal service is now up and running. This allows you to take control even when an exam doesn't go your way. So all you have to do to get the process started is head over to our website at www.carbonarc.co.uk, hit training, find your way to the Examinations Appeals Service link, read the description about what's available, start your application process, where we will be able to take some details from you about your exam and send you a PDF that will help bring everything together. At that point, we'll review your appeal, write an appeal document for you to send to your chosen scheme management committee, and hopefully get that examination redone.